So next we're going to look at what's called the binomial distribution. And you can almost imagine that the binomial distribution has something to do with the binomial coefficient. Essentially, the binomial distribution is quite similar to the hypergeometric distribution, with the difference being that we sample with replacement, meaning that in each new trial, like when we draw the second ball, the same probabilities still apply for drawing a blue ball, and that makes things a bit different. And now we want to take a look at that. And for that, we first want to take a look at the concept of a Bernoulli experiment, or a Bernoulli process. A Bernoulli experiment is a random experiment that is binary, meaning there are only two outcomes. Event A occurs or it does not occur, so success or failure. Let's take a look at a Bernoulli process. A Bernoulli experiment is a random experiment that is binary, meaning there are only two outcomes. Event A occurs or it does not occur, so success or failure. And the whole idea now is that we have a Bernoulli experiment where there's a probability p for success and a probability of 1 minus p for failure. And we do this repeatedly n times in a row. And each time we have exactly the same conditions, meaning precisely the same number of balls that we have. And we call that a Bernoulli process of length n. N was basically the number of times we repeat a Bernoulli experiment. And right, let's quickly introduce a few terms. And the occurrence of event A is often referred to as a success or a hit. So, when we say success or hit, we mean the event occurring, while the non-occurrence is considered a failure, the complementary event, so to speak. And the probability that the event occurs we call small p. So, we basically only consider p and not the occurrence, which would be 1 minus p, and we call p the probability of success or the hit probability. Alright, so that's a bit of preliminary thinking, and let's briefly consider what examples we have. As I said, we need to define whether something occurs or does not occur. And the coin toss is actually a really nice example because a coin toss is already binary, either heads or tails. So it naturally works out that there are two events or two outcomes. When rolling a die, it's a bit different. We have to think about what a hit means or what success is. And that could be, for example, that the number 1 is rolled compared to the number 1 not being rolled. And we'll do that because it makes it a bit clearer what p and 1 minus p are. Let's take this example and assume we have a die and we roll it 7 times in a row. So our n is 7. And our random variable is then how often event A occurs, or rather, how often do we roll a 1 when we roll 7 times? And what we want to do now is determine the probability distribution of this random variable. And you can see right away that it's a discrete random variable because we only have a finite number of outcomes. We can only roll a 1 a maximum of 7 times, which means the possible outcomes are obviously 0, 1, and so on up to 7. Alright, then let's calculate what p of x equals 2 is, and you can already see the result. Let's take a quick look at how we can derive that. So we have p, which is our probability. That's 1/6, and then we have 1 minus p, which is equal to 5/6. And then let's take a look. This term here. And what we see is that each die roll is independent of one another. So what happens is that this probability highlighted in red is now the probability that the first die roll is a 1, that the second die roll is a 1, that the third is not a 1, that the fourth is not a 1, that the fifth is not a 1, and that the sixth and seventh are not 1s. And then we simply multiply the probabilities of these independent events. Now, however, we've asked a different question, namely not that the first two are 1s and then the last 5 are not 1s, but we actually have more possibilities for rolling 2 1s. And we need to think for a moment about how many ways we can roll 2 1s. And that's 2 out of 7, because we have to choose 2 rolls where the 1 comes up exactly. So we have this probability here 2 out of 7 times, and that gives us our total probability where the 1 is rolled twice, but it's not clear or not predetermined at which positions these 1s have to be. And yes, that's 0.234. And now we basically understand the formula for calculating the binomial distribution, the probability distribution. Let's go ahead and do that. So we get the following values, and we can see that for 0, 1, and 2, it's relatively likely. And then starting from 3, it drops below 7%. And rolling a 1 7 times, as you can see, is very unlikely, with a probability of just 0.0025. And now we want to generalize this a bit. So what is the binomial distribution? Let's start by going through this text here. So in the first step, we have a Bernoulli chain, which means we have a random experiment that has 2 outcomes, and we perform it n times. So we have the probability p that it occurs, which is success, and then q, which would be 1 minus p. Exactly. And then we have, as always, the random variable that indicates the number of trials in which success occurs. And then we have this formula here, which describes exactly what we did earlier, where n was equal to 7. That was the number of repetitions. X was equal to 2. Exactly. And P was 1/6 and Q was 5/6. So it's the same idea that we can multiply these P's and Q's. Then that would be the probability that success occurs exactly in the first X cases and failure in the last n minus x cases. That's why we need to multiply by these binomial coefficients to account for all the possible ways that these x successes can occur. As I said, we call x binomially distributed, often referring to the parameters n and p, and we write x tilde bi for binomial distribution. And then NP exactly. And yes, it looks quite complicated again. Calculating these things can be tricky, and it would also be complicated to calculate the expected value and the variance. But actually these expected values are quite easy to calculate. Here we see the formulas. Let's first take a look at the expected value. That's really simple. It's just in times p. So in our example, for instance, n is equal to 7 and p was equal to 1/6. So 7/6 is the expected value, which is just a bit over 1. So it's really simple. And variance is also very easy to calculate, namely n times 5 times qp, which would then be 7 times 1, 6 times 5, 6. And then we have 35, 36, so close to first. The binomial distribution is tricky, in terms of probability distribution, but when it comes to calculating the expected value and the variance, it is easier. Recognize when a situation involves a binomial or hypergeometric distribution, calculate probabilities, and the expected value and the variance. And yes, so what should they take with them? So you should be able to recognize when a situation involves a binomial distribution or maybe a hypergeometric distribution, and then be able to calculate the probabilities, that is, the distribution, as well as the expected value and the variance by using the formula 2001. Alright, so those were the two discrete distributions we wanted to look at, and in the next video we'll take a look at the first and unfortunately the only continuous distribution we'll consider, which is the Gaussian normal distribution. Until then, take care.